Let us try to understand the concept of electric field. In the previous section, we saw that charges interact with each other. I take a positive charge and another positive charge, they repel each other. I take a positive charge and a negative charge, they attract each other. Now, the question is, why does a charge experience a force in the presence of another charge? Let us try to understand this. Let me take a test charge here. A test charge is a positive charge which has a magnitude of 1 Coulomb. Now, does this test charge experience any force as I place it here? Well, no. Now, let me remove it. Let me bring another charge Q out here. Has anything changed? Let us see. I bring the test charge here once again. What do we see? We see the test charge is experiencing a force and is moving radially outward. So what happened? When I brought the charge Q out here, it modified the space around itself, and the entire region where the test charge is going to experience a force is called as the electric field of this charge Q. And whenever any other charge is present in this electric field, it is going to experience a force. Now the question is, will the test charge experience the same force everywhere? Well, no. It totally depends on the electric field intensity. Now, what is electric field intensity? Let us understand it. Let me place the test charge here. It will experience a greater force. Let me place the test charge at some point here. It will experience lesser force. So, the place where it experiences more force, it is supposed to have a greater electric field intensity, and the place where it experiences a lesser force, it will have a lesser value of the electric field intensity. Now, what is this electric field intensity? Let us try to define it and get an expression for the electric field intensity. So, what is this electric field intensity? Now, let us take the test charge and place it very close to the source charge. Now, since the distance is small, by the Coulomb's law, the test charge is going to experience a very high value of force. So, I can say that at this point where my test charge has been placed, it is having a very high value of electric field intensity. Whereas, if I move my test charge and place it at a greater distance, then by the Coulomb's law, it will experience a lesser force. So, the electric field intensity at that point will also be less. So, I can summarize that points which are closer to my source charge will have high value of electric field intensity, and points which are far away will have a lesser value of electric field intensity. So let me define this electric field intensity for you now. The electric field intensity at a point is defined as the force experienced per unit positive test charge. It is denoted by the letter E, which is equal to F upon Q naught, and it has the unit of Newton per Coulomb.
Alright students, we have already learnt about the concept of electric field. In this part, we want to find out what is the electric field produced by a point charge. Right, we want to see the electric field due to a point charge. And then later on, we are going to see further more applications of this electric field. We will want to find the electric field produced by multiple charges, the electric field produced by charged bodies like a charged ring or a charged disk, etc. So let us first focus on the electric field produced by a point charge, because this will become the basis of all the other derivations, all the other applications. So let us consider a point charge capital Q here. Now we have already explained that any charge creates an influence around itself, which is what we call the electric field. And when in this electric field any charge enters, then it experiences an electrostatic force. So suppose that there is a test charge kept here. The test charge is represented by Q naught. I hope you remember, test charge never influences the system. The test charge is being brought only to detect the electric field. The test charge has a negligible magnitude and therefore it does not change the system. But the test charge, as soon as we bring it here, it is going to experience an electrostatic force, which will depend on the distance between the two charges. We know that if both charges are positive, then there is going to be a repulsive force acting on this particle in the direction of the position vector. And the electric field is also going to be in the same direction. Now, how did we define electric field? Just try to recall that. We have just now defined electric field as E vector equal to limit Q naught tending to 0 Fe divided by Q or Q naught. Okay. So let us just quickly recall what is the meaning of this. We said that the electric field at any point is the electrostatic force acting per unit charge on a test particle. So this is the definition that we are using. And this part, limit Q naught tending to 0, it just tells us that this is a test particle. Remember, this is a test charge, this is a test particle. Okay. So, this is the definition which we want to use to arrive at the strength of magnetic electric field produced by this point charge. So let us apply this. We already know what the electrostatic force will be acting on this test charge, right? We can apply Coulomb's law to find that force. So I can write that the electrostatic force is going to be K Q1 Q2, where Q1 is this capital Q and Q2 is this Q naught. So I can write it as K Q into Q naught divided by R square R cap. Because both are positive charges, electrostatic force is going to be in the direction of the position vector itself. If they were unlike charges, if one of the charge was negative, the direction of force will be opposite. Now, we need to put this force here in this definition of the electrostatic field so that we can find the strength of the electric field. So let us do that. I'll put this expression here and then we'll come back to the electric field. Therefore, I can write electric field is equal to limit Q naught tending to 0. This expression of force Q naught by R square R cap divided by Q naught, because there is a divided by Q naught here. Now, as soon as I do that, as soon as I write this, you can clearly see that the Q naught is going to get cancelled. So this Q naught term, this Q naught gets cancelled out. And therefore, this expression, this whole term on the RHS becomes independent of Q naught. Just observe this carefully here. This whole expression is now independent of Q naught. If it is independent of Q naught, then there is no role of this limit. If the variable itself is not there, why will we apply the limit? So this limit is also gone away as soon as we do this. And what remains is what we wanted to derive, that is the expression for electric field produced by a point charge. So the final expression that we get is E vector is equal to KQ by R square R cap. And this is the strength of electric field produced by a point charge. So we can see what are the parameters on which it depends. It is directly proportional to the charge Q. Definitely it had to be. So bigger the amount of charge, higher the magnitude of charge, more is going to be the electric field. Secondly, it depends on the distance. So there is the inverse square dependency here also, just like Coulomb's law, and that also had to be there. So greater the distance, weaker is going to be the electric field. If I go farther away from the charge, then the electric field is going to become weaker. The direction of electric field, that is also very important. We can see that the electric field will be along the position vector of the point where we are checking the electric field. But remember, in vector form, the charges always have to be put with sign. If it is positive, then positive. If negative, then negative. So if the charge is a positive charge, then the electric field will come in the direction of the position vector itself. But if the charge is a negative charge, then the direction of electric field will be reversed. So if I have a negative charge here and I am looking at the electric field at this point at some position vector R, then I am saying that the electric field will be in opposite direction. The electric field will be opposite to the direction of position vector. This is very important. So I can say and summarize in this manner, a positive charge has a repulsive electric field, whereas a negative charge has an attractive electric field. And that is what we are saying, because the test charge that we take is always a positive charge. So just imagine, if you forget, just imagine that there is a test charge, a positive charge kept at that point. So what is going to happen? A positive charge will repel it. So that is the direction of electric field. A negative charge will attract it. So that is the direction of electric field for negative charge. It is opposite to the direction of position vector. All right. So this is the expression which we wanted to derive, and direction also we have explained. Remember, this K is nothing but 1 upon 4 pi epsilon naught. You can write this as 1 upon 4 pi epsilon naught Q by R square R cap also. They both are the same things. In short, when we want to write, we just write it as K, but actual is of course 1 upon 4 pi epsilon naught. All right. So this was the very first and basic application of electric field which we wanted to see. We will continue exactly from here, and in the next part, we want to see how to find the electric field produced by a system of multiple charges. Okay students, so now that we have an idea about the electric field produced by a point charge, we can move on and find the electric field produced by a system of charges. That means we have more than one. We can have 2, 3, 4, 5 or n number of point charges forming a system, and we want to find the net electric field produced by such a system of charges. So how do we approach here? What do we do? So let's try to see the system first. Suppose that we have a test charge Q naught kept at some point P. So now we are saying that if there are multiple charges in the system, then this point charge will experience a force due to all of them. Suppose there is a charge Q1, then the charge Q1 will produce some electric field E1. Similarly, if there is charge Q2, then it will produce its own electric field E2, and then so on, E3, E4 up to En. So if there are n number of charges, each of them is going to produce its own electric field. But what do we do with these electric fields? So we say that the principle of superposition will be applicable here also, just like how it was applicable for Coulomb's force, or we can say the electrostatic force. So just this one point you have to remember. principle of superposition is still applicable. Principle of superposition is applicable. All right. So what happens in principle of superposition? Remember, there are two parts of principle of superposition. Firstly, when there are multiple forces involved, the individual force remains the same irrespective of the presence of other charges. So the interaction of Q1 and Q0 is going to remain the same. The interaction of Q2 and Q0 is going to remain the same. All the individual interactions will remain same irrespective of the presence of other charges. And the net influence or the net force will be the vector sum of all these individual interactions. That is what we did in the principle of superposition for Coulombic force. Same thing I am saying is applicable here. Also, the principle of superposition is applicable for electric fields also. And this can be proved very easily. Just write the net force on this charge and then apply the concept of electric field. We know that E vector will then be equal to limit Q0 tending to 0, the net electrostatic force Fe net, the net electrostatic force divided by Q0. And this net electrostatic force is nothing but the sum total of all the electrostatic forces acting on this individual charge. So what we will get is simply that the net electric field is the vector sum of all the individual electric fields. And that is the concept which we want to apply. But how do we visualize this? So this is simple vector addition, and we know if we have to add multiple vectors, then we have to add two at a time. I'll have to add E1 and E2 first, then we'll have to add the resultant of that with E3 and so on. Let's try to see that so that you get a clear view of how the net electric field will act on this charge. So I can say that E1 can be arranged anywhere. So I'm arranging it here. Now I need to place E2 with the tail coinciding with the head of E1 in this manner. And now we will have to find the resultant of these two vectors first. So let's say R1 is the resultant of these two electric fields. Then I will have to bring E3 and add it with R1. Once again, apply triangle law, head and tail are coinciding. Complete the triangle, we'll get R2. Then bring the vectors one by one in the same manner. Let's say we reach En finally. Then we will get the net electric field after adding all these vectors. So this electric field is the net electric field. Okay, this is the E net which we wanted to find. And if I try to show this here, then the net electric field is like this. So on this point charge, on this test charge, the net electric field is acting in this manner. This is the net electric field. And as I said, we can apply the principle of superposition to find the magnitude and direction of this net electric field. E net vector can be written as E net vector is equal to E1 vector plus E2 vector plus E3 and so on up to En. And how do we write the value of each of these fields? We've just now learned in the field produced by a point charge, it is KQ by R square R cap. So this is nothing but KQ1 by R square R1 cap, R1 square R1 cap. Similarly, plus KQ2 by R2 square R2 cap, and so on, continue till En, KQN by Rn square Rn cap. And this is how we find the net electric field acting at any point. Once again, remember the test charge is only brought to understand the electric field. There is no role of the test charge at the end. We can see in the final expression there is no test charge Q naught. So test charge has been brought once again only to understand the net force acting on the particle, net electric field acting at that point. All right. Once again, I would like to ask you to remember that here the sign of charge is very important. If the charge is positive, then the field will be in the direction of position vector. If the charge is negative, the field will be in opposite direction of that position vector. All right. So this is how we find the electric field produced by multiple charges, a system having multiple point charges. And this is all that we have in the case of field produced by point charges. In the next part, we will be seeing the electric field produced by continuous charge distributions. If we have charge distributed on, let's say, a ring or disk or a line and so on. All right. So this part is completed here. You can go ahead now and solve some problems based on this. Hello students, in this video we want to take some problems based on electric field produced due to point charges. So we've already studied the theory related to it. Now we want to see some application of it and some numericals and problems and even past year questions based on it. So let us go ahead and begin our topic where we want to take numericals on electric field due to point charges. So let's see the first question. This is our first question, first problem. The simple board level question, board level problem. A point charge produces an electric field of magnitude 5.0 Newton per Coulomb at a distance of 40 centimeter from it. What is the magnitude of the charge? So a simple question. There's a point charge, let's say Q here, and at some distance, which is given here as 40 centimeters, that is the distance we represent by R generally, the electric field is given to us. The strength of electric field is given to us. So we have to find what will be the magnitude of the charge. So formula for the magnitude of electric field is very simple. KQ by R square. Now, everything is given here. Q is unknown. So let me just rearrange this and write it this way. ER square upon K. And put all the values, solve and find the value of charge. So E is 5. The distance R is 0.4 meters. Remember, 40 centimeters is in CGS unit. We have to convert it and write it as 0.4 meters when we put the value. So 0.4 whole square upon K, which is 9 into 10 to the power 9 in SI units. So let's simplify. 5 into 0.4 will become 2. 2 into 0.8 will become 2 into 0.4 will become 0.8 by 9. This 10 to the power 9 I can send to the numerator so that it becomes 10 to the power minus 9. And this gives that charge is nearly equal to 0.09 into 10 to the power minus 9 Coulomb. Or in SI units, I can write it as 9 into 10 to the power minus 11 coulombs. Okay. Or I can say it is 0.09 nanocoulombs. So you should know different ways in which answer can be reported. Or I can say it is 90 picocoulomb, the factor of 10 to the power minus 12. So this is what we have. This is the answer that we get. The charge must be this much value, must have this much magnitude, so that the electric field is 5 Newton per Coulomb. All right. So this was a simple question based on direct formula KQ by R square due to a single charge. So let's take a little more difficult question. Let's go to the next problem. So this is the next question that we have. Again, it's a simple question, board level question, but a slightly different idea. A vertical electric field of magnitude 4 into 10 to the power 5 Newton per Coulomb just prevents a water droplet of mass 1 into 10 power minus 4 kg from falling. Find the charge on the droplet. So the setup here, if we want to represent, then it's like this. This is our water droplet. It has some mass, and obviously it has some charge because they're asking us to find that charge. So it has some mass m and charge q. Now they are saying that the electric field just prevents it from falling. That means the water droplet simply remains suspended mid-air. So how is this happening? This is happening because the electric force is balancing the gravitational force. So the electric force must be in vertically upward direction. The electric field must be in vertically upward direction so that it balances the gravitational force. So these are the two forces acting on that particle. There is the electrostatic force and then there is the gravitational force. All right. These must be equal and opposite to each other so that the particle, the water droplet, remains in equilibrium, simply suspended mid-air. So let us write the mathematical form for that. Fe is equal to Fg, the gravitational force. The electrostatic force can be written as QE, whereas the gravitational force, of course, we know is mg. We have to find the charge, so this will become mg upon e. Just put all the values, 10 to the power minus 4 into g value, that is nearly equal to 10 upon e, which is here 4 into 10 to the power 5, right? So 10 into 10 power minus 4 will become 10 to the power minus 3. Divided by 10 power 5 will become 10 power minus 8. So finally we have q equal to 1 by 4, that is 0.25 into 10 to the power minus 8 coulomb, or I can say this 2.5 into 10 to the power minus 9 coulomb, which is 2.5 nanocoulomb. And this will be the answer. This is the charge required on that droplet so that it remains suspended in air. It does not fall. It just remains stationary in equilibrium mid-air. So this is how we solve such questions. This question is basically based on Millikan oil drop experiment, okay, without really telling us that it is based on that. So this type of question is common in exams. They can also ask from this charge, find out what are the number of electrons present in it and so on. All right. So I hope this question was clear. It was a simple question. This type of question you can expect in board exam for 2 marks. All right. So let's go ahead and look at the next problem. Let's see the next question. All right, this is the next question that we have. This is from NCERT example 1.9. 2-point charges Q1 and Q2 of magnitude plus 10 to the power minus 8 and minus 10 to the power minus 8 coulomb respectively are placed 0.1 meter apart. Calculate the electric field at points A, B, and C as shown in figure. So point A is in between at the midpoint between those two charges. B is to the left of the positive charge and C is a point such that these three charges complete, these two charges and point C complete an equilateral triangle. You can see this is 0.1 meter, 0.1 meter, 0.1 meter, right? So let's go one by one. Let's look at the case A first and then we'll go to B and so on. So at A, if I want to show the electric field, then due to the positive charge, there will be a field in this direction towards the negative or away from the charge. Positive charge always produces a repulsive field, whereas negative charge will produce an attractive field. So the field due to the other charge, the negative charge, will also be in the same direction. And therefore, the net field will be the sum total of these two fields. So the field at A is equal to E1 plus E2 vectorically as well as in terms of magnitude, it is just E1 plus E2 because they are in the same direction. So we have kq1 by r square plus kq2 by r square. Now you can clearly see that the charges have same magnitude. Both have the same magnitude. This distance is also same for both. It is 0.05 meters. And therefore, these two magnitudes of the electric fields will be same. And I can simply double up the field. So now let's put the values 9 into 10 to the power 9 into the charge, which is 10 to the power minus 8, upon the distance, which is 0.05 meter whole square. So this is what we get. Now, if I simplify this 10 to the power 9 into 10 power minus 8, if we do, it will simply become 10. So this 10 power minus 8 will go away with this 9, only 10 will remain. So we have 90 upon, this will become 0.0025, which I can also write as 25 into 10 to the power minus 4. Okay, because this is 5 into 10 to the power minus 2. So this is what we get, and this, if we want to simplify, we'll get EA is equal to 90 upon 25 will become 3.6, and this will go to the numerator and become 10 to the power 4. The unit will be Newton per Coulomb, and this will be the electric field that we get. This is due to one charge. So we need to multiply this by 2. Remember, there were 2 charges. So we need to multiply this whole thing by 2. And actually, we'll get 7.2. So 7.2 into 10 to the power 4 Newton per Coulomb is the electric field at point A. So this part is done. And this was easy because both the fields are in the same direction. We just have to add them up, their magnitudes directly. Okay. So let us go to case B. I'll remove all this calculation. We'll need some space. So I'm removing it. You can note down everything. Let's go to the case B. For case B, now if I analyze, then due to positive charge, of course, there is a repulsive field. And also we need to see here and observe here that the positive charge is closer to B, unlike the A case, where both were equidistant. So positive charge is closer, negative charge is far away. So the field due to negative charge will have a lesser magnitude. And at B, now if I want to write the net electric field, then vectorically it is the sum E1 plus E2. But in terms of magnitude, it will be E1 minus E2 because they are in opposite direction. E1 minus E2 will be the net electric field. So let's do the calculation now. I'll have to write KQ1 by R1 square minus KQ2 by R2 square because the distances are now not same. They are different. So just put the values. K is common. K I can take out common and say that 9 into 10 power 9, this is the common factor outside. Q1, Q is also same. So that also I can take out common into 10 to the power minus 8. But the distances are different. This distance is 0.05. That is the same as previous question. But this distance now is 0.15. You can see this is 0.05 plus 0.1. So it is 0.15. 0.15 whole square. Okay. This term again simply will become 10. So this whole thing I can say will become 90. So we have 90 into 1 upon 0.05 whole square. So as we had said, this will become 1 upon 25 into 10 to the power minus 4. 1 upon 25 into 10 to the power minus 4. This will become 1 upon 225 into 10 power minus 4. Okay. So 10 to the power minus 4 also I can take out common, 25 also I can take out common, and what will remain is 90 upon 25 into 10 power minus 4 into 1 minus 1 by 9. Right? This will become 8 by 9. I'm writing here itself because there is a little less space. So let me write it here itself. This will become 8 by 9. 9 and 90 I can cancel. This will become 10. So we have 80 upon 25. Okay. 80 upon 25, which will become 3.2. And this 10 power minus 4 will go to the numerator and become 10 power 4. So it will become 3.2 into 10 to the power 4 Newton per Coulomb. And this will be the electric field at point B. You can see it is lesser than what we got in case A, which was 7.2. And that is because here the fields are getting subtracted. Their magnitudes are getting subtracted. All right. Now, let's go to the case C and see how to find the field at that point. That is a little different. So again, I'm going to remove all this so we can focus on the field at C. So at C, if we observe, then the direction of the fields will not be along the same line. Due to the positive charge, there is a repulsive field like this. Due to the negative charge, there is an attractive field like this. And now I cannot simply add or subtract the magnitudes because the vectors are in different directions. What we can observe though is the symmetry is still there. This distance is 0.1 meter. This distance is also 0.1 meter. So the distances are same. The distances from the charge, up to that point C are the same. And therefore, even at C, just like case A, the magnitudes of E1 and E2 are same. And let me say that it is some E, because of which the solving will become slightly easier. This angle is 120 degrees. See, this is an equilateral triangle. So 60, 60, 60, this is 120 degrees. Two vectors, when they are at an angle of 120 degrees and their magnitudes are equal, the resultant equals this magnitude itself. And therefore, I can say that the magnitude of electric field at point C is equal to E itself, which is KQ by R square, where R is the side of the equilateral triangle. So let's put the values 9 into 10 to the power 9 into the charge, which is 10 power minus 8, upon the distance, that is 0.1 whole square. So in the numerator, we'll have 90.1 square. When we take to the top, it will become 2 more zeros and we'll get 9,000 Newton per Coulomb. This will be the electric field at the point C. There's even lesser. We can see at point B, we had got 3.2 into 10 power 4. This is 0.9 into 10 power 4. So this is even lesser because only certain components of the field are getting added. If we see, only these components are getting added. These vertical components are getting cancelled out. From parallelogram law also, we can see the resultant electric field is like this, right? Parallel to this line AB, or parallel to the line joining the two charges. So I hope this question was clear to you. Actually, we have solved 3 questions here. Different points we have taken and found the electric field at these respective points. So this type of question is very common, and you can get any setup, multiple charges, 2, 3, 4 charges, and you can be asked to find field at any point. But generally, there will be some symmetry which we have to utilize. All right. So let's go ahead and take the next problem now. All right, students. So this is the next question that we have. This is from NCERT example 1.8. An electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude 2 into 10 to the power 4 Newton per Coulomb, as shown in this figure A. the direction of the field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance as shown in figure B. Compute the time of fall in each case. Contrast the situation with that of free fall under gravity. All right. So now if we try to understand what is happening here is this electric field is acting like how gravity acts on particles. See, for the proton, this electric field is going to give a force in the downward direction itself because proton is positively charged, and we know that F, the electrostatic force, is equal to Q into E. This is a vector relation. For the electron case, field is upwards, but still the force is going to be downwards only. Okay, the force is still going to be downwards. As I said, negative charge. So the force is in opposite direction of electric field. Field is upwards, force is downwards. Now, if there is a force, then there is going to be an acceleration also. So the acceleration produced in this case will be equal to QE by M. That is in the direction of the in the direction of the force. Now, in this case, you can see that the force acting on the particle is not dependent on the mass. Unlike gravitational force, it is dependent on the charge. But acceleration is dependent on the mass. Okay. In case of gravity, we see that the force is mg and the mass is m, so the m gets cancelled out and the acceleration is always g. The same for both the cases. Whereas in this case, the acceleration will be inversely dependent on the mass. So the acceleration will be lesser for proton and more for an electron. So the acceleration for electron is greater than the acceleration of proton. So actually I have answered the second part here. Contrast the situation with that of free fall under gravity. What they want us to do is compare the two cases. So in gravity, what happens is any particle you take, you release them, they free fall with the same acceleration, because of which they reach the ground, they cover the same height in the same time. Whereas here in this case, we are seeing that the acceleration is not going to be the same. Lighter particle has more acceleration, heavier particle has lesser acceleration. Okay, because of which the time is also going to be different. To calculate the time, we just need to use the second equation of motion. Simple, very simple. Second equation of motion. Because we know the initial velocity is 0, we have the acceleration as calculated here by this formula, and we know the distance through which it is falling, 1.5 centimeters. So let me just call it as some height h. So S is equal to ut plus half at square, and S here is h, u is 0, half. Acceleration as we have calculated here, it is QE by M. Okay. So here this acceleration, only magnitude we need to take because the direction we have already adjusted. So the direction is downwards and this t square. So if we rearrange this, we will get that the time period so the time taken by the particle to fall will be equal to 2mh, okay, upon QE under root. So as we had expected, greater acceleration means lesser time. So the lighter particle is going to take lesser time to fall through, and the heavier particle is going to take more time to fall through. After this, we just need to substitute all the values, but be careful of the units and the values of the charge of particle and mass of particle. All those values when you put, then you will get the time taken to fall through in this case. Okay, So for example, if I want to calculate for electron, then the values will be like this. 2 mass is 9.1 into 10 to the power minus 31. H is 1.5 centimeters, which is 0.015 meters upon charge, which is 1.6 into 10 to the power minus 19, and electric field, which is given as 2 into 10 to the power 4. So you'll have to put all these values, simplify. It's a very lengthy calculation, but here for practice, you can use a calculator and find the answer using a calculator. When you do that, you will get that the time taken by the electron to fall through is 2.9 into 10 to the power minus 9 seconds. And similarly, when you substitute the mass for proton, so instead of this value, you will have to take 1.67 into 10 to the power, it's not completely clear here. So it will be 1.67 into 10 to the power minus 27 kg. So when you put this value instead of the mass of electron, you will similarly get the answer for the time taken by proton, which as we said will come out to be more, and it will come out to be 1.3 into 10 to the power minus 7 seconds. And these will be the two answers. Clearly we can see the time taken by electron is lesser, time taken by proton is more, as we had expected. And we've also compared this situation with the free fall under gravity. They do not take the same time. The time depends on the mass because electric force depends on charge rather than mass. So I hope this question was clear to you. And this type of question can also be framed based on how we have projectile motion in motion under gravity. So instead of the vertical field, if we have or instead of leaving the particle, if we project the particle horizontally or if we project the particle at an angle, then it will go like a projectile. All right. So let's move on to the next problem now and see what do we have in store. All right, so now I want to take some problems from previous year papers, some problems which have appeared in KCET and even medical entrance exams in the previous years. So let's see, let's take the first question. This is a question from KCET 2017, so very recent question. 4 into 10 to the power 10 electrons are removed from a neutral metal sphere of diameter 20 centimeters placed in air. The magnitude of the electric field in Newton per Coulomb at a distance of 20 centimeters from its center is. Okay, so in such a scenario, some electrons, if they have been removed from the sphere is going to become positively charged. And how much will that charge be? That we can calculate by Q equal to NE. Put the values 10 to the power 4 into 10 to the power 10 into 1.6 into 10 to the power minus 19. This will give 6.4 into 10 to the power minus 9 Coulomb. Now, if we have a sphere of diameter 20 centimeters, then the point which they are talking about at a distance of 20 centimeters from the center is going to lie outside the sphere. Okay, it will be somewhere here. Because if diameter is 20 centimeters, then the radius R is only 10 centimeters. And this distance is 20 centimeters. So this is the radius. Let me write it as capital R. This is the distance where we want to find the field. Now, the electric field due to a sphere, due to a charged sphere, is exactly same as how we have the field due to a point charge. Okay, we need to use this result here. The derivation of this is seen later, but here we need to use that. So we can write that the electric field is simply KQ by R square. Put the values 9 into 10 to the power 9 into 6.4 into 10 to the power minus 9. Distance is 20 centimeters, which has to be written in meters. So that is 0.2 meters. So we'll have 0.2 whole square. Simplify this. This will become 0.04, and this 10 power 9, 10 power minus 9 gets cancelled. So we have 9 into 6.4 upon 0.04, which will become, this can be written as 640 upon 4, which will become 160. So 160 into 9, which gives me 1440. Unit is, of course, Newton per Coulomb, SI unit. And we can see it matches with option D. And that will be the correct answer. So a simple question, you can see it's direct formula application, only one extra step. We just had to find the charge by using the number of electrons. And as I've said before also, the questions which come in competitive exam need not be very difficult. They are generally simple, they can be direct, just a little extra effort and simple calculations. You can see the calculation is also very easy, not really difficult. You can do it mentally in your mind. So this is how questions have appeared earlier in KCET. I hope you understood this question. It was fairly simple. Let's go to the next problem now and see what is that. This question will be the last question that I want to take in this segment, based on electric field due to point charges. This is taken from AIPMT 1990. So a very old question, but this type of question is very common even in JEE exam. So let's try to understand what the setup is. A pendulum bob of mass 30.7 into 10 power minus 6 kg and carrying a charge 2 into 10 power minus 8 coulomb is at rest in a horizontal uniform electric field of 20,000 volt per meter. Volt per meter is the same as Newton per Coulomb. Don't worry about it. The tension in the thread of the pendulum is. So there is a horizontal uniform electric field. Now we have seen what happens when there is a vertical electric field. So there is an extra vertical force either downwards or upwards. But if there is a horizontal electric field, then the pendulum will have a tendency to get shifted towards the right. So what is going to happen is this. Let me try to draw the setup. So let's say this is our support, and initially the pendulum is like this, vertical. But because of the electric field, it is going to get deflected and it is going to come here. And this is what is happening in this question. This is the initial position. This will be the final position. Okay. Now, why is this happening is because there are two forces. Let's say this is some positive charge plus Q, and there is an electric field E here. So due to the gravitational force, due to gravity, we have a gravitational force in vertically downward direction like this. Whereas due to the electric field, we have an electrostatic force in the horizontal direction. This is Fe. This is the gravitational force Fg. You can see that the tension will have to balance the resultant of both these forces. So if the resultant force is here, tension will have to get aligned in such a way that it opposes these two forces. So the tension will act in this direction, balancing both the forces. So tension will act like this. Mathematically, if we want to write what will be the value of tension, then you can see Fe plus Fg, when we do, they are at right angles. So their resultant will be under root Fe square plus Fg square. And we are saying that tension will have to balance this. So the only thing that now we have to do is find these Fe and Fg. the electrostatic and gravitational force. Fe is equal to QE, where Q is 2 into 10 to the power minus 8 coulombs. E is 2 into 10 to the power 4, which gives me 4 into 10 to the power minus 4 newtons. Fg, the gravitational force, if I calculate it, is simply mg. Mass is 30.7 into 10 to the power minus 6. G is to be taken as 9.8. Now, 30.7 into 9.8 can be approximately taken as 30 into 10, which will become 300. So we have 300 into 10 to the power minus 6, which will give Fg equal to 3 into 10 to the power minus 4 Newton. So this is the gravitational force, this is the electrostatic force. Put these values here and find the tension. We can see what we are going to get is 10 to the power minus 4 will come out common. In the root, we'll have under root 3 square plus 4 square, a very common Pythagorean triplet, which is going to give 5. And this is what we get, 5 into 10 to the power minus 4 Newton. Option C matches with that, which is the correct answer to this question. Okay. So this is the general form for which we are writing the tension. You can also get the question to find what is this angle here. That can also be calculated. Try it out. You'll see such questions later in the assignment also. So I hope this question was also clear to you and you've gotten an idea what type of questions can come in competitive exams. All right. And this completes our questions based on electric field due to point charges and uniform electric field in general. All right. So I'll end the session here. I hope everything was clear. You can go ahead and do some practice and then move on to the next concept.